Chapter 5 is about systems of equations. So the first definition we should talk about is what is a system of equations, and it's simply a combination of multiple functions. So those could be linear or nonlinear, and Chapter 5 is going to show us how to solve systems depending on which type of functions we are looking at in the system. Today's method is on graphing, so we can either look at the table of the graph or the actual graph of the system and then find a solution. So our first example gives us a table for two different functions, and the first function is y equals 9x plus 1, and the second one is y equals 3x minus 2. Notice that the x column is the same, meaning this is where the x value is, and this is the y value for 9x plus 1. At negative 1.5 for x, then negative 6.5 is where the function 3x minus 2 is. So when I'm looking for a solution, I'm looking for the ordered pairs to be matching. So if I notice I have negative 3.5 listed twice right through here, meaning that that would be the same y value at the same x value. So a solution to any system is an ordered pair, so our ordered pair here would be negative 0.5, negative 3.5, because that is the only place in the table where they have the same y values given the same x values. So that would be our solution to the first one. Since these are both lines, we could actually look at the visual of that and we could graph it. So if I looked at y equals 9x plus 1, if I start at my y-intercept of 1 and then a slope of 9, that would be up 9 over 1 or down 9 over 1. That would give me a line that is very steep. So I can go ahead and graph that, so we can take a look at that first line. Then I could also graph y equals 3x minus 2, again starting with a y-intercept of negative 2 and a slope of 3, which would be up 3 over 1 or down 3 over 1. And this is still pretty steep but not quite as steep. So I could look at this line, and that will be the line for there. And so if you notice, what I'm looking for is the intersection of these two graphs, which is going to happen somewhere over here. Okay, somewhere in here. And so if I were to read my graph, that would hopefully be negative 1/2, negative 3.5, like it showed us above. However, with these graphs being kind of hard to read, I'm not sure that I would ever been able to pick out negative 1/2, negative 3.5, which is the accurate answer from this graph. So sometimes it's nice to use the table, sometimes it's nice to use the graph. This at least gives us a visual of where that intersection would occur. However, finding the exact from the graph is many times challenging, unless of course it happened at a nice integer. Otherwise, sometimes the table again is nice. A downside of a table is if I asked you to find this, not given a table, and you had to look through a table, I'm not sure you would ever start looking at halves, or maybe it was a quarter or a third. So those are some of the plus and minuses of these first two methods. Sometimes I can actually ask you to work backwards and say, okay, is negative 2,5 a solution to the given system? So in order to answer that question, I would just plug in negative 2 and 5 for my x and my y value, because that's an ordered pair. So I could plug in negative 2 for x and 5 for y, and if I get the 1 that the equation says I would, then that would work. So 2 times negative 2 is negative 4 plus 5, well that indeed is 1. So that would be correct. So this would equal 1, so that would be a good thing. But it would also have to work in the second equation. So if I plug in negative 2 and 5 for x and y here, then I'd have 4 times negative 2 plus 5. So 4 times negative 2 is negative 8, plus 5 is negative 3. And that does not equal 3. So then that would not be a system because it works in the first equation, but it does not work in the second. So my answer would be no, negative 2,5 is not a solution because it does not work in the second equation. So you always have to make sure that you're checking both, because in order for it to be a solution, it has to be true in both of the different equations. Our next example, again, is going to ask us to graph. So if they ask us to graph, then that is going to give us a visual, and hopefully then it would be able to be maybe an integer answer, unlike our first one. But the problem with the way these are written right now is they're not in y equals. So these are in standard form. So if you wanted to, you could do your XY table and do your staggered zeros, or we could solve these each for Y. So if I solve the first one for Y, my first step would be to subtract 3x, and then I would divide by 2, so I'd have Y equals negative 3/2 x plus 6. So then I could go ahead and graph that at a y-intercept of 6, and a slope of negative 3/2 would be down 3 and to the right 2, or up 3 and to the left 2. So then I can graph that line with a negative slope over here. I'm going to draw my line all the way through because I'm not sure where that other graph is going to go, so I am not sure where it's going to intersect. My other one, if I solve for solve for y by moving that over, I would get y equals x minus 4. So I can plot that with a y-intercept of negative 4 and a slope of 1, which is up 1 to the right 1, up 1 to the right 1. And then that line would intersect about there. So based on my graph, it looks like they would intersect right here, which would be the ordered pair 4, 0. Now the nice part is that I could check my answer by plugging it into the equation like we did in that last example. So if I plug in 4, 0 for my first equation, I get 3 times 4 plus 0, which is 12. And in the second equation, if I do 4 minus 0, that is 4, so that indeed does work. So this would be a nice example of where the visual is a nice, quick way to find the intersection point of 4, 0. My second equation now would also need to be solved for y equals. So I could do that by adding the y and subtracting the 12, so that would give me 9x minus 12. So when I plot that, my y-intercept is negative 12, so that's down a little bit. I'll just kind of guesstimate there. Up 9 over 1, and then up 9 over 1 is a very steep line again. So I can look at this very steep line here. Again, drawing that line all the way through the graph, the coordinate plane. And then the next one is already in slope-intercept form, so that's nice. So that's 9x plus 6. So that would be starting at a y-intercept of 6. And then I'd have to go up 9 into the right one, but I can also go down 9 and left 1 to get a similar, or to get the same graph, just graphing a little bit easier based on my coordinate plane. And that would be what that graph looks like. So this is a nice way to kind of look at these two, because if I'm looking for the place in where these lines are going to intersect, I don't think they're ever going to cross. And I would notice that because the slopes are the same. So last chapter we talked about if the slopes are the same, then the lines are going to be parallel. Well, parallel lines are never going to intersect, so there's no solution to this ordered pair, or this system of equations, because they're parallel. If this had turned out to be overlapping lines, like if this red line had landed right on this blue line, then I would have said that there's infinite solutions because it would have intersected at every single point in the coordinate plane. So anything with the same slope and different y-intercepts, meaning they're parallel, will be a no solution. If they had turned out to be the exact same line, so if I had solved this and this had a plus 6, then they would have been in infinite solutions. Okay? Our next example is going to be y equals negative 3x plus 7 and y equals 4 over x. So the first one is a line, but the second one is a hyperbola. So this is from chapter 2 that we were just studying. So finding exact ordered pairs on this curve, so if you remember, that would be a hyperbola, and that would be in quadrants 1 and 4. And I know I would have the ordered pair 1, 4 and negative 1, negative 4 on that, but I'd have some curve here, and then I would have my line 3x plus 7, so I could start at negative 3x, so down 3 and to the right 1. But I think that that would be pretty hard to figure out exactly where those are going to intersect there. If they're going to intersect, I'm not sure, because hyperbolas are kind of hard to graph exactly. So if I have something that is not linear, I'm going to suggest that we go to our graphing calculators. So let's go into our graphing calculators, and we can graph two equations at the same time. So our first one is going to be negative 3x plus 7. And then instead of hitting enter, if you just go down, now I'll have f2 of x, so then I can type in my 4 over x and hit enter, and now I can see my two graphs. And I can see that the blue line and the green line, the blue and the red are going to intersect. However, that's a little hard to see, so I'm going to try and zoom in to that area. So I'm going to zoom in here, over here, to kind of see what's happening. And I might try and do this one more time. And I actually think if I get these out of the way, it intersects once down here and once up here. So it looks like 2 points of intersection. So what we can do is we can find that point exactly by using our calculator. So if we go to Menu, Analyze Graph, there's an option that says Intersection. So if I look at intersection, I'm gonna get this vertical line, and what I want to do is I want to highlight where they overlap, where they intersect. So I always want to start on the left side. So when I get this vertical line, I can click and I'm going to drag until they intersect, and if you notice, the ordered pair pops up, and then I can just click again. So it's telling me that up here it intersects at the point 1, 4. So one of my solutions is 1, 4. Now to get this one, I'm going to do that process again. So Menu, Analyze Graph, Intersection. Now I can't start way over here on the left because it's going to keep giving me 1, 4. So what I need to do is start on the right side of 1, 4, but the left side of where I am, so somewhere over here, and then click and drag down here, and then I'm going to see my other ordered pair at 1.33, 3. So those are going to be my two solutions over at my system. So I would have 1, 4 and 1.33, 3. Okay, so you can round to the nearest hundredth when you get a decimal. That is completely acceptable. So now let's go ahead and try this next one. If we notice, this first one's going to be a parabola, and the second one is going to be a hyperbola again. So if I look at my parabola, that would go through 1, 3 and -1, 3. If I'm just trying to think about some easy numbers to give me a quick sketch, just so I kind of know what to expect on my calculator. And then 10 over x again will be 1, 10, -1, -10, and that's going to be the curve here and the curve down here. So this time it only looks like I'm looking for 1 point of intersection in the middle here. So if I go back to my calculator, I can go back to kind of get maybe a normal window. So maybe I would start by going Menu, Zoom, Standard, and that would kind of get me back to my normal window here. And then I can hit Tab and I can arrow up, and that's where I can change my equations. So this time I'm looking for 10 over x, and my first one I'm looking for 3x squared. If I remember that right, 3x squared and 10 over x. Yep. Okay, so I did again know that it was going to intersect somewhere up here. So now I'm going to zoom out again. So Menu, Zoom Out. And I want it to be way up here, so I'm going to center it up here, and I'm going to click, and that's a pretty good view, so I'm going to hit Escape so I don't keep zooming. So again, I want to find this point of intersection where the red and the blue line cross. So I'm going to go to Menu, Analyze Graph, Intersection. I'm going to get that dotted vertical line. I'm going to put it to the left of where they cross. I'm going to click, and then I'm going to drag over that point of intersection. So this one crosses at 1.49, 6.69. This is a great example of when technology can help. If I had asked you to graph this by hand and try and find that, or even in a table, I think that would be nearly impossible. So when systems are not linear, they're curves, we're going to use our calculator. Otherwise, we should be able to use some of those other methods to solve it. So this is 1.49, 6.69 for our answer. 1.49, 6.69 for your answer, because you're always looking for an intersection ordered pair for your solution to a system. If you do not have the Inspire, your steps are going to be a little bit different. So I will post a different how-to on Canvas as well for you to find that using your calculator.